the mechanical engineer needs to know about it, and also the civil engineer also needs to know about it. And what about metallurgy people? Right? So they need to study properties of those materials and like which material you are going to use it for these shock absorbers. Right? So the material engineer is going to give the properties of those materials, whatever which were used in it. So next.
Shift plus అదనుకుంటా.
Yeah. And next, let's come to electric circuits. You might have seen these circuits in physics itself, right? What is a circuit? LC circuit, right? Let us say initially I have given some voltage to it, and now the current is flowing in that circuit. And what is the voltage drop due to inductor? And that will be proportional to its the rate of change in current, right? So voltage drop due to inductor you can see, and voltage drops due to capacitor, that will be proportional to its charge, right? So you can see that the system equation governed by the system will be L into di by dt plus q by c. L into di by dt which represents voltage drop due to inductor, and the next one represents the voltage drop due to capacitor, right? And you might have seen one more system here. What is it? LCR circuits, right? In which here the extra component which is added is a resistor, right? And what is voltage drop due to resistor? By using Ohm's law, you can know that it is V equal to IR, right? So the one extra component is added here, right? When you give some external voltage E of t, and that will be equal to the sum of the voltage drops here. Due to inductor is 1, due to resistor is 1, and due to the capacitor is 1 more, right? So now you know that the rate of change in charge is nothing but current. So now if I replace the I with dq by dt, you'll end up with a second order differential equation with constant coefficients. So if you want to know the current flow in the circuit, you need to know how to solve these differential equations, right? Next. Yeah. Do you find anything wrong in this picture? Maybe it's not visible to the people, like those who are sitting there. Next slide. Yeah. Can you find anything wrong in that circle? Yeah, there is a creep deflection if you see. Okay, there is a deflection in the beam, like it bent a little bit if you observe that. Okay, so if you are a civil engineer, if you are making construction, you should make sure about the deflection in beams. You cannot simply randomly construct a building with beams as you wish, right? One should calculate what are the loads which are acting on it, or how the loads are distributed throughout the beams. Otherwise, what happens? The disasters can happen, right? So here, let us see how to see the deflection in beams and the differential equations for these deflections. Okay. So first, I'd like to calculate the bending strain. If you have a concrete disc, okay, not a disc, it's a rectangular box. You assume that either it is a concrete material or an iron material, like whatever. You just take a rectangular box. Now I'm going to bend that box. Okay, so when you bend it, what happens? So there will be bending strain and bending stress will come. Right? So now how to find that bending strain and bending stress? So here you see the picture. So initially, the AB picture you can see, that is what the initial picture, and this is what after bending. Okay. So here when you bend it, what happens? On the top layer, the compression is going to happen, and on the bottom layer, the expansion, the tension is going to happen. Right? It means on the top layer, the length is going to be decreased. On the bottom layer, it is going to be increased. Right? So here, but at the middle, or maybe you can find one layer at which there is no change. On top it compressed, and on bottom it is expanded, but in middle you can find that there will be no change. It means the length remains same. Right? So here I am interested. Now you take a circle along that line AB. Okay, you create a circle and you locate a center of that circle. Okay. So here I am interested in knowing what is the arc length of CD. When you bend it, what is the arc length of the outer layer? So how do you calculate arc length? From circle, you know, right? When you know the angle and the radius, then you can calculate arc length by just r times theta. So here, next. So R plane formula is R times theta, and let me assume that R represents the distance from the center to A. Okay, because we created a circle using that layer AB. Okay, that's a distance from center to A. So now that arc length can be R times theta, whereas what is the arc length for CD? When I assume that the distance from that layer AB to CD is y, okay, now the total radius will be R plus y. Okay, so now the arc length for CD will be R plus y times theta. Now bending strain can be calculated by taking change in length by its original length. Right? So you can see that the bending strain for this one is y by r. And what will be the bending strain? If you multiply this bending strain with its elasticity, then you're going to get the bending strain. Right? Next. And here you can see some differential equations which occur when you study about these deflections in beams. Okay. So this is one equation which tells about deflection in beam. You can see that E is the elasticity of the beam. Right? For different materials, you'll have different elasticities. Right? And I is the moment of inertia of cross section. And of course, to calculate moment of inertia, one needs to use integration. Using integration, you're going to calculate them. Right? And next, where m represents the bending moment. So if you want to calculate the bending moment, so that is the equation which gives the bending moment. Right? And if you want to know the shear force, what is shear force? When you bend a beam, there will be two forces which are going to act. One is a horizontal one, and another one is a vertical force. Or when you slide two plates, there is going to be some force which is going to occur. Okay. So now when you bend it, there will be a vertical force which is going to act on it. So, okay, and that force we are going to call it as a shear force. Okay. So to calculate shear force, you can differentiate that bending moment, that will give you shear force. And whereas if you differentiate one more time, and that will give you the deflection, not the deflection. Next. Yeah. So here, let's assume that we have a beam which is parallel to the x-axis, and I'm going to act some load on that beam. Okay, some load is given to that beam. Assume that that load is not a constant one, it is a function of x. Here I have a thick density, whereas here I have a less density. Okay. So now I'd like to study how this load is distributed along it. Okay. So and that is a differential equation which gives the load distribution. That's load distribution will be equal to the second derivative of the bending moment. Okay. So when you know that this E and I are constants, then it will become a fourth order differential equation. So now you need to know the solution of this fourth order differential equation, right? So, and of course this equation is easy to solve. How do you solve it? On the right hand side you only have function of x. If you just integrate 4 times, you are going to get y, right? Next. And that is the formula for shear force. Next one. Yeah. See here we'd like to design aircrafts. When you design aircrafts, one should know what are the loads which are going to act on wings or the entire body, right? When it flies, you can see how the other forces are going to act, right? So, like, however you have studied the load problems for civil one, here also you need to study the same things. Okay, maybe little different. Here, the material engineers are going to give you the properties of the materials which were used, right? And the aerospace engineers are going to, they are going to derive those differential equations. Those are the differential equations for one particular wing. Okay. I'd like to just show the differential equations, the occurrence of differential equations at different places. Okay. This is one. Next. And many aircraft models are designed with mathematical modeling. Okay. So using MATLAB simulation and all, you can design the aircraft models. Okay. You can simply Google it, the aircraft designs using mathematical modeling. Okay, you can get some information about it. Next. Yeah. Then look at it. I'd like to look at the center of gravity. Okay, so how do you calculate center of gravity? For example, if you have some area, the area is shown on the peak, right? So here I'd like to look at the center of gravity. So what is the x coordinate of x coordinate of center of gravity, and similarly y coordinate of center of gravity. These two we need to find. Okay? So you need to integrate the the variable y over the area. Then you'll get the qy, and if you divide it with a, that is going to give you x coordinate of center of gravity. And similarly, you can calculate y coordinate of center of gravity. When you keep x comma y, that will give you the location which shows the center of gravity. Okay. Next. Yeah. In future, you are going to see integrating over a region. So far, you have seen integration over an interval, isn't it? Have you integrated over a region, over a surface? Those are the things you are going to learn in future. So here is one problem. You might have seen this problem in physics. When you throw a object upwards with some velocity, right? So how do you find its equation? The equation of motion. Right. So here we will end up with a differential equation. And what kind of differential equation is that? dv by dt plus c by m into v of t equal to minus g. That is a first order linear differential equation. And you know how to solve the differential equation, right? Finding its integrating factor, then you will simply write its general solution. Right? So our life is always easy with linear differential equations. Next. Yeah. And what is that? What is that? Can you see? Like the last row. There is some tank and some chemical compound is entering into the tank. And similarly, we are sending the water outside of the tank with some other pipe. Okay, so we have a tank which has both inlet and outlet, and we are sending some chemical compound, some contamination to that tank. Okay, so when you send it, I am interested in knowing what is the contamination concentration after some time. Okay, let us assume that you keep on mixing and you are sending the solution out from some other pipe. Okay, so what will be the concentration? Let's see how to derive the concentration here. So let me assume that x of t, which represents concentration of the contamination at time t. Okay. So now the rate of change in concentration will be given by the rate which is coming in minus the rate which is going out. Okay, that will give you a differential equation. So the differential equation will be given by dx by dt equal to Rn minus R. And let's assume that x naught is the initial concentration. Yeah, here I got you one model. You can understand like at what rate the chemical is coming in and at what rate the chemical is going out. So here you can see that the 2 grams per liter we are giving it, and which is coming at a rate of 10 liters per minute. Okay, let's assume that the water in the tank is 100 liters. So now I'd like to calculate the rate which is going out. So how do you calculate? So you see first what is the concentration per liter, right? How many grams of concentration is there? We don't know. That we would like to calculate. That is what x by 1000 into, and the rate which you are sending out. Let's assume that we are sending that water at 10 liters per minute. Okay, so now you'll end up with a differential equation. And how do you solve that differential equation? You can use variable separable method, or you can see that as a first order linear differential equation, right? So when you deal with multiple tanks, you'll come up with second order differential equations. But here most of the problems you'll find it in first order differential equations. Yeah. And the partial differential equations, you might have known just what is partial derivative or how to calculate partial derivatives. Okay. But here in future, if you want to study problems related to heat or heat diffusion, let's say if you have a plate and you're heating it. Now I'd like to see what is the heat diffusion throughout that plate. Okay. So now we'll assume that u of xyt, which represents temperature at the position x comma y at time t. Okay. So the heat diffusion equation will be given by dou u by dou t equal to dou square u by dou x square plus the rest. Okay. Now you should know how to solve this differential equation. And this is not a completed problem, because just I gave you the equation, but there are something which we need to make sure, that is initial conditions, what are the initial temperature, okay, and what is the temperature at some particular time, all that we have to make sure. So now we need to know what is the solution of this differential equation, what are the classical methods. If classical methods doesn't work, then what we have to do, that we have to think. Okay. Another one, Navier-Stokes equations. These are also partial differential equations. Okay. Yeah, don't be panicked by looking at these differential equations. Once if you move to the topic, once if you understand what are the concepts which are there, it will be easy to you. Okay. The only reason if you feel fear, you are not familiar with it. That's all. Once if you get familiar, you'll feel free with these expressions. Okay. So these Navier-Stokes equations which occurs when you study a fluid flows. Okay. And also if you want to estimate the flood, let's say the heavy rains came on north side. Now there will be flood which is going to come here, right, to the south region, right? So now we'd like to make that estimation. So there you can, these Navier-Stokes equations will be helpful. Not only there are many regions in which these equations will come. Okay, and this is a particular equation for viscous flow. If you take an incompressible fluid, for viscous flow you can find this equation, Navier-Stokes equation. Yeah, why the transfer calculus was written there? See, we'd like to study the solutions of these differential equations. Right? Let us say the classical methods or whatever methods we have learned that doesn't work. Then what do? We look for an alternative. Okay. So we move from time domain to frequency domain. And there, when you move from time domain to frequency domain, there the things will become easy. Maybe a differential equation here will become a linear equation there. It is easy to deal with Ax plus By equal to C and Ex plus Dy equal to F, right? It is easy to solve that equation. Once if you shift your domain, we are not comfortable here, then we'll move to other place. And there we'll get things, then we'll get back here. Okay, the same thing happens in transform calculus. There are integral transformations you have, those are called Laplace transformations and Fourier transformations, fast Fourier transformations, and all. And these are extremely used when you solve problems related to control systems or signal processing. Okay, for example, your mobile networks and all. There you need the help of Laplace transformations and fast Fourier transformations. And of course, when you study those subjects, you'll get a doubt whether I'm reading the core subject or mathematics subject. You'll get that doubt because most of the things you'll find it there in mathematics subject. Okay.